This element has a weird title. It's how statistics behave. It's important to understand what would happen if you spent the rest of your life repeatedly sampling the same thing over and over and over again. Because then that will tell you what you can expect when you actually take only one sample. How many times do you do a study? A study, you do it one time. But in order to understand what's going to happen when you do a study, you have to think about what would happen if you did things an infinite amount of time. So we need to think about this idea of a distribution of statistics. And I know this sounds like gibberish the first time you hear it, a sampling distribution of statistics. Well, let's build this up. Remember, what is a statistic? And Tony, are you still filming this?
I'm still filming.
Oh, good. Do you remember what a statistic is?
Oh boy, don't ask me.
Okay, good. A statistic is a number that describes your sample. That's all that it is, a number that describes your sample. So, for example, a mean. A mean is a statistic. Okay, good. So check. You can calculate a mean for every sample that you take. So you go to Home Depot, you grab 10 light bulbs, and you can calculate the mean number of hours that the light bulbs lasted, right? That's a mean. How did you get that sample? Well, you just went in and you said, I'll take 2 of those, 6 of those, 4 of those, and you get your 10 light bulbs. That was a random sample. So that statistic, sorry, I'm getting excited about this. That statistic itself is random. The mean itself is random. And if the mean is random, we can draw a distribution of the means just like this. Just like we drew a distribution of elderly Chinese people who showed up at a health fair in Chinatown. So this distribution, this curve, is called a sampling distribution of a statistic. If you took all samples of a given size from that population and you calculated the mean again and again and again, this is what you would get. Now, luckily, we don't have to do this. We know what this will look like, but this will be the theoretical distribution of every possible sample that comes out of that population. It's kind of like this. Here's a population of people, all right? You take a bunch of them, you calculate the mean, and then you plot the mean, maybe it's here. You take that same population, go back, sample again, calculate the mean, and it drops in here. Same population, take a different sample, calculate the mean, and it drops in here. If you did that an infinite number of times, you would get a curve that looks like this. In other words, how means behave. Remember that stupid slide that I had that had like the lettering on it and you had a population here and then you had a sample here and I drew that arrow? How the means behave is this way. But now we're going to go and say, what does that tell us about the truth, about where the population is? So this is important. You have to stop thinking about the mean as a specific number. Like, it's true that the mean exists. For a given sample, the mean exists. But you have to ask yourself, why did I get that mean? Why did I get an average of 992 hours from my light bulbs? Well, it was random. If I took a different sample, I would get a different mean. Why did I get that different sample? Because it's random. This is really important. The mean is a random statistic. Just like we said, I don't know what I'm going to get when I flip a coin 50 times until I flip it 50 times. You don't know what mean you're going to get for your study until you actually do the study. And if you do it right, it will be based on some random chance-governed mechanism. We will pick up here and think about what this distribution looks like. Thank you.